Testing, testing. 1, 2, 3, 4. Testing, testing. 1, 2, 3, 4. Okay, hi everyone, welcome to today's machine learning class. And today we will talk more about the theory of generalization. But before we do that, we have some leftover from last week's class that we need to finish. And if you remember, last week we started talking about whether machine learning is feasible, whether we can really get the test performance or the out of sample performance estimated while doing something in sample, while doing something on our data. And we mentioned that it's not possible if we don't have any assumptions. But if we include some assumptions, for example, the assumptions we included is that training data and test data is related by a distribution. We sample from that distribution and we use a bin model to try to describe the sampling process, and then use Hsuan-Tien's inequality to mathematically tell you what's happening there. And Hsuan-Tien's inequality tells us that we can estimate the portion of orange marbles within the bin by sampling, and we extended to the learning scenario last time. Okay, so that's a little bit recap about what we did. And today we'll continue from there. Okay, basically, last time we mentioned that learning is possible if we have a finite number of hypotheses. But unfortunately, most of the hypothesis sets that we encounter in the real world is of infinite size. Okay, so therefore, we need to spend a lecture or maybe two trying to conquer this issue. Okay, how can we deal with hypothesis sets that's of infinite size? Okay, that's the focus of today's class. Okay, before we start, let me quickly see if we have any questions to answer on Slido. Okay, let's see. I'm trying Slido's present mode to see if it can be more friendly for everyone. Okay, so good morning. That's good. Upload the slide at least a day before. Actually, we uploaded the slide yesterday, but not exactly 24 hours away. Okay, my apologies for that. Usually, the reason for delaying the uploading of slides is because I want to add some new content, shuffle some of them, and so on. As you can see, most of the slides are similar to the MOOC version. Okay, so if you really want to print something, you can use the MOOC version. I modify from there, but if you want to wait for the full slide, I'm as deadline driven as any of you, okay, and therefore I try to upload them the previous night, but I cannot guarantee that I'll do so 24 hours away or even longer. Okay, great. Okay, and I think we have collaborative note here. You are welcome to take it. Now let's get started with today's class. Okay, as we mentioned, we've run through lots of things about the model. Okay, the bin model and so on. Okay, so let us start from here, maybe. Okay, just to refresh your mind. Last time we talked about what it means to be good or bad. Okay, and we say that if we have a good data on hand, it actually means we can use the data to verify any hypothesis in our hypothesis set. Okay, so if we say a data set is good, it means the evaluation on H1, good, evaluation on H2, good, evaluation on H3, good, and so on. Okay, so it needs to be good for every hypothesis. Otherwise, if it is bad for any of the hypotheses, okay, then we say that the data set is bad. And what we're trying to do is to try to bound the probability of getting a bad data set. Again, a disclaimer. We don't know if the data set on hand is good or bad. We don't know. We just want to mathematically bound the bad probability to be small so we can have a high belief, have a good belief that the data set on hand is good. Okay, so that's the logic. Okay, we're not using this Hopkins inequality to say whether the data set on hand is good or not. We don't know. Okay, but what we can do is to say, with a high probability, you will get a good data set. Okay, so it is reasonable for us to believe that the data set on hand is good enough and continue with the learning process. Okay, so that's the motto here. And how do we bound the bad probability? Okay, the bad probability that any of the hypotheses may not be the best match for our dataset, or our dataset may not be the most representative one with respect to the hypothesis. Okay, so we write down the definition here saying that, okay, bad dataset means it's bad for any of the hypotheses. Okay, that's why we're using or here. Okay, and this or represents the events, okay, that we're interested in, and they may be overlapping, they may be non-overlapping, and so on. The worst case, okay, for this probability to happen, okay, think about each of these events as occupying a portion of in the probability space, okay, in the event space. Okay, so this is a circle, this is a circle, and so on. Okay, so calculating the total probability when those events are union together is like calculating the overall area occupied by those. Okay, and what we can do is to decompose those areas to individual ones and sum them. Okay, this is because the worst case is that we get non-overlapping areas and we need to count them one by one. And this is called the union bound in probability. When using the union bound, then we already have this individual term. Where did we get the individual term? The individual term came from Hopkins inequality. Okay, each hypothesis is guaranteed by the Hopkins inequality to have a upper bound on the bad event. So we can sum them together, and then we get the n factor that grows or that makes the original Hopkins inequality slightly worse. And we call this the finite beam version of Hopkins. And similar to the original Hopkins inequality, now we can use it for when E out is not known to us. We cannot use it in scenario where we don't need to get F, we don't need to get P, but we can get some guarantee about the upper bound on the bad event. Therefore, we can state that E in equal to E out or close to E out is probably approximately correct. Okay, that was what we did last time. And now that you see the inequality, you should know that given that we can use the data sets with a high probability to verify any of the hypotheses, then the reasonable choice is to pick the lowest E-in hypothesis. Much like what we did in perceptron learning algorithm, we picked the line with the lowest E-in, which is 0 in that case. Okay, so that brings us to the statistical learning flow that we can now introduce to you. Basically, it adds to the original learning flow an unknown probability distribution. Okay, think about this as the assumption that we have. And this assumption ties the training examples and the way that we're going to evaluate the final hypothesis together. Okay, so through the probability distribution, we get the original training example, and on the very same distribution, we evaluate the final hypothesis. We evaluate the possible E out. And by having this probability distribution, we guarantee that E in is going to be close to E out. And therefore, our algorithm can just focus on minimizing E in. Then we can get a low E out in the end. Okay, that's the new learning flow. of course, we're still doing this under the assumption that the hypothesis set is of finite size, and also the number of examples is large enough such that our bound on the right-hand side, the 2n exponential, blah, 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 and there's the n here, would be small enough, okay, so that we can believe we have a good data set on hand. And then if A finds a hypothesis such that E in is nearly 0 or is very low, then there's PEC guarantee for E out to be close to 0 as well. Okay, that's the so-called statistical learning flow that justifies learning is possible from the statistical perspective. This is not the only perspective that people studied in machine learning. Okay, if you go to other machine learning classes, okay, some people tell you the more probabilistic perspective. Some people tell you more about the online decision-making perspective, and so on. Okay, so different machine learning models have their different perspective about how machine learning is possible. But in this class, we will mainly use the statistical perspective to introduce you many of the popular learning models. And in this perspective, we are basically dividing the learning problem to two parts. One is training. We need to ensure that E in is small, okay, or here we're saying close to 0, but if you think about the noisy case that we will encounter later, maybe we want to make E in as small as possible. And the other part we decompose to is that we want to make E out close to E in. Okay, so this guarantees that we have a decent test performance as well. And both are somewhat important, okay, to ensure that our ultimate goal, which is small E out, can be achieved. So these are the two central questions, and these two central questions can actually be summarized in one sentence, and I intend to use this sentence to tell you a little bit about what we covered in the previous 3 lectures. In lecture 1, we say that the goal of machine learning is to make G close to F, okay? Or in our current definition, it actually means we want E out to be close to 0. And also in lecture 1, we introduce you the perceptron learning algorithm that can guarantee E in to be close to 0. Actually, with some assumptions, E in is exactly 0 when we run the PLA algorithm. Now, after knowing this too, we say that, okay, this is a particular case in machine learning that we will encounter frequently in this class called batch and supervised binary classification. Similar analysis can be carried out on other learning problems as well, but we will not go through them one by one in this class simply because it's not a theory-oriented class. Okay, but batch supervised binary classification is arguably one of the most analyzed machine learning problems in the history, and we use it as the foundation that we introduce you the machine learning theory. And then in the previous lecture, lecture 3, we achieve this, okay, or basically we connect the dots by introducing the statistical flow that assures with a high probability that E out is close to E in. Okay, then we basically achieve the goal that we had in lecture 1 along with the algorithm and by the statistical learning flow. Of course, there is a big if, okay, that we still have it here, needing M to be finite. Okay, and that's something we need to fix, okay, in order to make this whole sentence work. But I just want to give you the big picture first. So we split learning to 2 central questions. Can we ensure that E out is close to E in? And this is generally called the testing part, or sometimes we call it generalize. Okay, generalize means being able to extend from what you see in the data to what you haven't seen. Okay, in Mandarin Chinese, it is 举一反三. Okay, so 举一 means give you one example, and 反三 means you can extend it to 3 other cases that you haven't seen. Okay, so this is the question about generalization. Actually, this is the topic we're going to talk about a lot in today's class. And then there's a second question about how we can make E in small enough. And this is typically what's happening in training a machine learning model or in a typical machine learning algorithm. And to make an objective value small, it is the area of optimization. So in the next lecture, starting in the next lecture, we will introduce you some optimization algorithm within the machine learning model. So you know we have tools that can make E in small enough. And in these two questions, I want to quickly go through what role the hypothesis set plays for the two questions. One, can we make sure that E out is close enough to E in? And two, can we make sure that E in is small enough? If we have a small hypothesis set, from Hofstad's inequality, it is good for the very first question because the bad probability is upper bounded by something related to n. So if n is small, then we can make sure with a high probability that E out is close to E in. But when n is small, it generally means you only have a few choices in your hypothesis set. So maybe in those very few choices, you do not find anyone with a low E in. Because if you have so few choices, okay, then maybe for all of them, the E in is super high and so on, and you cannot find a hypothesis with E in small enough. So small n is bad for the second question. How about large n? Well, it's the opposite, okay? Yes, if you have a large hypothesis set, you have many choices, and then maybe you can really find a hypothesis with low E in. Okay, generally you have a higher chance of this happening simply because you have many more choices. But, okay, in terms of the first question, then the answer may be no, because the bad probability now grows with n. And therefore, unless you have sufficient number of examples, okay, remember here the exponential bound, there's the negative n in there. So if you have enough examples, then you can knock down this bad probability to a small value. But if you don't have enough examples, then you are doomed with the first question. So this tells us that using the right n, or basically the right hypothesis set, is important. And we haven't touched n equal to infinity yet, because it may sound like a large n here that is doomed. Okay? But that's what we're going to do today. Okay, we're going to show you for some hypothesis sets, even if the size of the hypothesis set is large, okay, is of infinite size and so on, the effective number of hypotheses within the hypothesis set may not be that many, and we can still have some learning guarantee. Okay, but for now, let's just remember this bound hints us the trade-off in machine learning. The trade-off in machine learning basically tells you that you need to select the right hypothesis set, or the hypothesis set with the right size, or later we will change the size to complexity, with the right complexity, so your machine learning can perform well. And as a preview, this is what we're going to do today. We proved this bound, okay, with a finite n. Now we're going to replace this finite n with a quantity, and I put a question mark here because now after I insert the quantity, maybe the inequality needs to be changed in some way and so on. But basically what we're going to do is for every hypothesis set, we're going to derive a corresponding quantity that replaces big N. And I'm going to call this quantity the small n. Why am I calling it the small n? Because hopefully it's smaller than the big N, which can be infinity. Big N can be infinity, but small n, we insist it to be a finite quantity that we will derive later. And if we successfully do so and have this kind of bound, then we can have some learning feasibility even for infinite big N. And we will study this little mh, okay, I'm calling this little m and sometimes accompany it with h to highlight that it's a quantity derived from the hypothesis, so we can understand the trade-off for the right hypothesis sets. And after we do all this, hopefully we will be able to answer why the perceptron learning algorithm that we studied in lecture 1 can actually have some learning guarantee. Okay, let me quickly summarize what we have done last time before we go into the questions. Okay, last time we started with the impossibility of learning, okay, saying there's no free lunch outside of the data set. But if we introduce some statistical guarantee, we can have some pack statistical assumption, then we can have some pack guarantee outside the data set. And we use this to derive the verification flow for a single hypothesis and then the learning flow for a finite number of hypotheses. Okay. Using this, we decompose learning to two central questions, one for testing, whether E out is close to E in, and one for training, okay, whether E in is close to 0. Okay, that was what we done last time. And now let's see if we have any questions. Okay, so some of you are saying that the sound today is a little bit louder and coming with some noise. Let me adjust it a bit. Okay, sometimes it's just because sometimes it's just because I speak too loudly and basically went above the limits of the microphone. But let's see if things get better if I adjust the volume of the microphone. Okay, and also let me unplug the microphone and plug it again. So maybe, okay, there's nothing better than a simple resetting, I guess. Okay, so that's the sound part. Let's see if we have some questions. Okay, what we need is EL is close to in to approve our assumption or our model works. Okay, what we want is E out to be small. Okay, think about E out as the ultimate evaluation that we want to have in terms of the similarity between G and M. What we want is E out to be small. Okay, but in general, what we can do on hand is about E in. Okay, so the way we use to justify that E out is small is try to connect E out with E in. That's why the central question is whether E out is close to E in. Okay, if E out is not related to E in at all, then we are somewhat doomed, okay, because any good performance that you see in E in cannot translate to good performance in E out. Okay, so we use our assumption, our statistical assumption, to make the connection between E out and E in, so we can reach our ultimate goal, which is E out to be small or E out to be close to 0. Okay. I'm wondering that if we pick an overfitting hypothesis E in to 0, does it contradict E in similar to E out? For the results that you see now, no. If you can actually get an E in equal to 0 hypothesis within your hypothesis set, which is of finite sets, and your M is small enough with respect to maybe your big N, then it's not overfitting. At least you don't know whether it's overfitting. Okay, so basically what we're trying to do here, we're not studying overfitting, whatever. We're just trying to justify why picking the minimum E in may work. Later, after we go through all the theory, we will actually see the root of overfitting, and we'll discuss that later. That happens very frequently in machine learning and so on, but not now. For now, we're just doing something simple. We're picking the lowest E in hypothesis, and we want to know why it may work. Okay, at least we're trying to see the more optimistic cases, okay, where we can guarantee E in to be close to E out, and say that our approach of picking the minimum E in, which is usually called empirical risk minimization, by the way, okay, saying that we're picking the one with the smallest E in, and we're justifying that this could work. Okay, can the format of our cancellation be unified? Some didn't write clearly their corresponding time session and the compensation one, which, okay, actually, I really have trouble understanding what this question is about our cancellation on what? I'm a little bit confused. Okay, so if you could please try to restate your problem in some other way, or send us an email so we can interactively clarify this. Okay, but for now, I have to say that I have trouble understanding what's being asked within this question. Okay, why large M cannot make E out close to E in? I'm kind of confused. Okay, let's check the bound that we get here. Okay, we are trying to bound the bad probability. Okay, so there, and if you see the bad probability, in the bad probability, there's an N there. Okay, let's say you have a 2 here, and let's say by the number of examples that you have on hand, you have something close to 0.01 in this term. Okay, so then you have 2, you have 0.01 that multiplies to 0.02, looks good. But now, let's say you have N equal to 40, okay, which looks like a large number. Then what happens? It says your bad probability is 0.02 multiplied by 40, that's 0.8. And bad probability less than or equal to 0.8, which means you only guarantee to get a good data set 20% of the time, which does not seem too good. Okay, so when N is too large, then you essentially have very little guarantee about the bad event. Okay, if you have very little guarantee about the bad event, then you are highly uncertain whether E out is close to E in. Okay, that's what we have within the bound that we get. Okay, great. Allow me to switch a bit. I remember we had a discussion that we should also switch to the recent mode, so some recent questions gets answered. How can I get the inequality on the top of Hangout P30, page 33 from page 28? Okay, let's see. Page 33 from page 28. Okay, page 33 and page 28. Basically, the bound on page 33 is exactly copying the one on the top is exactly copying page 28. This is P bad. Okay. It's a little bit tricky. Okay, now I notice where the confusion may come from. Originally, we derived the probability of getting a bad data set. Okay, the probability of getting a bad data set actually means the data set is bad for any of for some of the hypotheses. Okay, not all of the hypotheses, but for some of the hypotheses. Now your algorithm chooses a hypothesis from the hypothesis set. Therefore, you actually have the probability that E in minus E out is greater than 0 on G, which is the hypothesis of your choice, is less than or equal to P bad D. Because there are two cases, right? You actually, with your the data sets that you have, you actually pick a bad hypothesis. Okay, then the events are the same. But sometimes, okay, the data set happens for some hypothesis, but you didn't pick it. Okay, you pick the hypothesis that's sufficiently good with respect to the data set. Okay, then the event doesn't happen. Okay, so there's a relationship of less than or equal to here, and then the one on page 28 gives you the bound. Okay, so I see where the confusion is coming from. It's actually because we removed one slide, and that was the connection slide that I forgot to mention. And thank you for asking this question. What if we have the bound greater than 1? Does it mean we should modify n or n? Very good question. And the short answer may be yes or no, but allow me to answer this question maybe a lecture later. Sometimes, okay, it's hard to modify n because we cannot gather more data. Sometimes we don't know which n we're having here. Okay, we can make n smaller, we can make n bigger, but we don't know the exact n. So modification is usually not what we do. And as we will see later, this bound is practically not very meaningful because it is arguably very loose. When a bound is loose, you easily get the probability, the upper bound of the probability to be greater than 1 unless you have millions of examples. Okay, so those are some tricky issues about the gap between theory, the bound that we see here, and practice. Okay, the results that we need to have in practice. So bear with me for a lecture or two before we get into that about what we do in practice for those. Okay, yeah, there's a similar question about what happens when the value is high. Actually, 0.5 is not high, but 0.8 or 1 or even higher is really high. Okay, what if E out is higher than E in? Okay, what does this mean? E out is higher than E out is in practice commonly higher than E in. Okay, that's for sure. But we're just trying to bound the difference to make sure that it's not overly higher than E in. Okay, you don't want to train a stock predictor where you believe to be of 1% error rate, but you send it to the market and find that it's 40% error rate. Okay, it's just not what you want. So what we're trying to do is to guarantee that, or try to have a probabilistic guarantee that it's not much higher than E in. Okay, but in general, it's doomed to be higher than E in simply because you are just observing a few examples on hand. That's your E in, and you are trying to ask the machine to generalize to lots of different cases, much like us in life, right? Okay, for situations that we have seen, we typically do better than on the situation that we haven't seen. Okay, so very typically, E out is higher than E in. Can we take E in and E out as training error and test error? And yes, and that's actually the name that people often call those. Okay, except for test error, sometimes people have a different name because E out is used to indicate the ultimate test error where you have an infinite size of test set, while the test error is often used to mean the error on an independent test set. What kind of function we can use weight to close in? Okay, I assume that you mean what kind of function can we use the weight vector, like what we did in the perceptron learning algorithm to approximate. Okay, generally we will discuss the property that we need to have on the hypothesis set later. So weights are just parameters of the hypothesis set, and we will see what properties we need to ensure for those hypothesis sets to work. Okay, great. Now we are having a more moderate size of audience online, and we can afford to answer most or all of the questions. I think that's actually a great mode to continue with our teaching. Okay. Now, let's see. Allow me to change the slides to today's. Okay. Wait, why is this the old one? Let me check. Sorry, I opened the wrong file. This one. Okay, so now let's get into the theory of generalization, basically trying to extend the results that we had to infinite number of hypotheses. Before we start, I designed a motivating example, okay, that we'll actually encounter a little bit later to try to convince you that even when there's an infinite number of hypotheses, learning can be feasible. Let me clarify the setting that we have here. Okay, first, we consider the input space to be a finite range. Okay, so imagine that you have a line of numbers here, and there's a range of -1 and 1. Okay, and that's the 0 here, and assume that we're going to sample our x, our inputs, uniformly, just one-dimensional within that range. That's our inputs. And we will take a target function that's sine of x, okay? Saying that basically whatever is positive or 0, okay, I'm going to assume 0, okay, the 0 part corresponds to +1, and the negative part corresponds to -1. Okay, so still binary classification that we had considered. That is, okay, basically what you will see is that you get a bunch of data sets, okay, uniform ID sampled within the range, something like this. Okay, on this line, you will get a bunch of examples that are positive and a bunch of examples that are negative. Okay, and the label of those numbers are basically comes from the target function that's unknown to the machine. Okay, so think about, you get circle, you get cross, that's the thing you feed to the machine learning algorithm. Now what you want the machine learning algorithm to do is to decide a threshold that classifies the +1 against the -1. Okay, so much like what we're doing in perceptron learning algorithm, but now one-dimensional. Okay, so you can imagine, okay, your cutoff hypothesis may be something like this, okay, and this threshold would be named big A here, okay, as the threshold of dividing positive and negative. So the hypothesis set that you have contains all the hypotheses of this form. Okay, so if A equals 0.1, you have a hypothesis. If A equals 0.1126, you have another hypothesis. If A equals minus 0.2, you have a hypothesis. So you have many hypotheses. How many do you have? Your A, your threshold, can be anything within this range. right? Okay, basically you don't know what your target function is. Okay, so you have a hypothesis set, but you know that your data is going to be generated within this range. So why not just set the threshold within this range? But even within this range, you have an uncountably infinite number of thresholds, infinitely many. So that corresponds to our case where we have an infinite number of hypotheses. And I'm going to tell you a particular learning algorithm that's relatively easier to analyze. What this algorithm does is, starting from the examples that you observe, it checks all the positive examples and pick the smallest positive example as the threshold. Okay, so basically, this is how this particular algorithm decides the threshold A star. Okay, the algorithm picks this threshold as the hypothesis, or basically the G chosen by the algorithm is just H parameterized with this particular threshold. You can see that this means E in of G equals 0. Right? Okay, because we assume that anything above the threshold is positive. Above 2 or equal to the threshold is positive by assuming sine 0 equal to positive 1. Okay, now this is a particular case, and I want to argue that for this particular case, there's learning guarantee. There's guarantee that E out can be small. Why is that? Okay, let's see when E out would be big. In particular, let's see when E out would be bigger than some epsilon, okay, which is a value that's less than 0.5 for mathematical reasons, but we don't need to worry about details now. Let's just try to analyze how big E out can be. Now, if E out is bigger, let's first see how we calculate E out. Our ideal threshold, our F, is at 0. That's F. Our E out is here. Its G is here. So the difference between F and G, let's see. If any example is above the threshold of G, G would say positive. F would say positive. F would say positive. No error. If anything is less than 0, F would say negative. G would say negative. No error. The only thing that G and F disagrees on is the region between 0 and A star. Therefore, E out of G is just A star divided by 2, because we're doing uniform sampling within -1 and 1, and therefore the probability density in each part is 1/2. Okay, so E out of G is just A star divided by 2. So if E out of G is greater than epsilon, then A star must be greater than 2 epsilon. That actually means after you do the sampling, okay, you never get any example that are 2 epsilon within 0. Okay, you never get anything that's between 0 to epsilon. After you do uniform sampling again and again and again in this range, no, you never get anything between 0 and 2 epsilon. That's the only case where you can have E out greater than epsilon. Okay, what's the probability that this happens? So you have a region that you do IID sampling, but there's a zone that you never step in. So the probability that this happens means every example that you get are outside of the zone. So the probability here and the probability here, which is just 1 minus the probability in this range, which is 2 epsilon divided by 2. Okay, so now you get some bound. Okay, the probability that you get something really bad is that you never get any example, any positive example that's within the range of 0 and 2 epsilon. And if that happens, your E out will be super big. But the probability that this happens is small because this is a value that's smaller than 0. You are doing exponential, so this is exponentially decreasing. For example, let's say the probability of this is 0.9, but you are doing 0.9 to the 100 times. Okay, with a high probability, you would get an example that is close enough to 0. That's the positive example close enough to 0 that you can use as the threshold to guarantee that your E out and your E in will not be too close to each other. So bad data can still happen rarely, even for infinitely many hypotheses. That's what we try to illustrate here. Try to give you some faith that what we're going to do next is something possible. Now, to actually solve this problem, let's first look at where we get n in the first place. When we get n, we get it through the bad events. Okay, let me name them Bn. Okay, it says for an individual hypothesis, something bad happened. E out and E in are not close enough to each other. And to give being A the freedom of choice, okay, we want everything to be good. Okay, so if on any hypothesis the bad event happens, then we say it's bad for the whole hypothesis set, and we use the union bound. Okay. As hinted, the union bound is an overestimate, especially for many cases where n equal to infinity. Why is that? For example, in what we have illustrated, we have many hypotheses that are very similar to each other. For example, in the threshold, if my threshold is 0.1, the other threshold is 0.1126, they are close to each other, and therefore, whatever data set that's good or bad for those two hypotheses, they are good for both or bad for both. So the bad events are overlapping or the good events are overlapping, but in any case, we should not count them as two separate pieces. For those two hypotheses, their E outs are similar because they are close to each other, and their E in are similar because for most of the examples, okay, maybe you cannot differentiate their differences. So the example that we illustrated with an infinite number of thresholds highlights that although we have an infinite number of thresholds for thresholds that are really, really, really close to each other, they are not distinguishable. And therefore, the picture about bad events should be more like this. All the regions, all the circles overlap with each other, and we're counting, we want to estimate the overall region. If we want to estimate the overall area, the overall region, then we should not do so separately. Union bound does so separately, resulting in gross overestimate that cannot handle the case where we have an infinite number of hypotheses. But for now, to get a more meaningful bound, we need to try to account for the overlapping nature of those events. And the way we're going to do so is to group similar hypotheses by kind. So now we're not interested in the number of hypotheses. We're going to be interested in the kind of hypothesis. Okay, so that's the new concepts that we're going to introduce next. Now let's think about this. Okay, we are now familiar with perceptrons, which can be visualized in a 2D space by all lines. How many lines do we have in a Euclidean plane? On a Euclidean plane? Infinite, right? But if we think about it, if we only have one input vector on hand, and we're trying to evaluate, okay, all the possible lines with respect to this single input vector. How many kinds do we have? Let's see. We have one kind being, okay, this line where this side is positive, and this particular line says circle. We have another kind of line, maybe something like this, okay, and the positive side is here, and this particular line says this example is cross, it's negative. Just two kinds, okay. The lines that are that predicts a circle and the lines that predicts a cross. So there are other kinds of similar lines. For example, this line is supposedly similar enough to the first line simply because from this single example, if we just watch from the eye of this single example, we see circle. So my claim is that there are just two kinds of lines on this plane with respect to one input vector. One called positive and the other called negative. That's what we're going to do to group the line. We're going to group the line with respect to the number of input vectors that we observe. If you understand Mandarin, it means 以管窥天. And I'm not being any impolite to our president of NTU. I'm just saying, okay, there's something that we use to check all of the possible lines. And this something, this 管 here is the input vector that we're considering on hand. So if we are looking with, we are just checking with respect to one input vector, we just get two kinds of lines. Let's continue the exercise. How many kinds of lines if we view all of them from two inputs? Okay, one possible line, circle, circle. How do we draw this kind of line? Here, circle, circle. Now, another kind of line, circle, cross. How do we get this kind of line? Circle, cross. Another kind of line, cross, circle. How do we get this kind of line? We can reuse the orange line, but with an opposite direction. And the fourth kind would be cross, cross. How do we get this line? We can reuse the green line, but in another direction. Okay, so now we get through two inputs, there are four kinds of lines, okay? And what I was doing was to try to draw lines, but we can also simplify this by drawing the patterns on the two inputs. Okay, so one pattern, circle, circle, one pattern, cross, cross, one pattern, circle, cross, one pattern, cross, circle. So we can get four different patterns. One input, two patterns or two kinds, two inputs, four kinds. How about three inputs? Okay, let's check three inputs. How many can we get? We can get, I imagine you are sufficiently good with combinatorics, and you see that we can get all 8 possibilities. Okay, 3 circle, easy. 3 cross, easy. And actually, you notice the symmetry I'm putting here. 2 circles on this side, easy. 2 circles on this side, easy. And 2 circles on this side, easy. And there are symmetry cases as well. So 3 inputs, 8 kinds of lines. Now, my question is, are there always 8 kinds of lines for 3 inputs? Let's check another case. If we put the 3 inputs on the same straight line, okay, so basically in Mandarin it means 3点共线. Okay, so if those can be connected by 3 straight lines, then what happens? I get 3 circles. Yes. I get 2 circles for the first 2 points. Yes. I get 2 circles for the last 2 points. Yes. Now, can I get this? No, 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 because you cannot just draw a straight line. Of course, it's very hard me to draw a straight. Actually, I can do that with a tool. So there's, let's see. Okay, maybe I draw this straight line, but this straight line would say this is circle, these two are cross. I cannot achieve this pattern. So there are patterns that cannot be achieved if we put the inputs in some special positions. That's important to know here. So basically, in those cases, instead of having 8 possible kinds, we only have 6 possible kinds for these 3 inputs. Okay, so that's about what I want to play with for the easy cases where we have a few points and ask you how many patterns that we can get from those points. Let's look at another case that you need to do. Okay, what you need to do here is to have 4 points, and I'm not making them collinear or anything. I just put them, think about them in the corner of the squares or something like that. Okay, so basically putting the 4 inputs in 4 corners and try to ask, okay, how many kinds of lines are there for 4 inputs? How many patterns can we generate with lines for 4 inputs? And now this is your task. We're going to take a 10-minute break, okay, where you can work on this task and provide your answer on Slido. And we will continue with our Q&A and also discussion from there after the 10-minute break. Let's start with the 10-minute break, and I'll set up Slido soon for this. Okay, welcome back. We have seen the responses from many of you. Thank you for your active participation. And let's see. Okay, let me close the poll first. And how do I see the results? View results. Okay, I'm not sure if you can. Okay, let you see this more. Okay, so you should be able to see the results here. Many of you chose 14, and there are other answers, okay, that people choose as well. What we will do is as follows. Okay, so basically this is a tradition of this class, and I actually see many of you, some of you actually, not many, some of you giving answers more than 14, okay, which is the majority answer. And I'll explain what we mean by 14 here. And if you believe you have a super good answer that results in a number greater than 14, then please let us know your approach through Slido or through email. Okay, you can send an email to me, and I'll provide a reward for that. Okay, so basically the reward that I'm going to provide is that you can decide for people who choose 16, actually, for people who choose 16, the reward that I'm going to give you is that you can decide the homework grade of every homework of yours in this class. Okay, so that's a reward. So if you think you have a super good answer explaining why 16 is possible, please post on Slido or send an email to me or something. And I mean, this is broadcasting, so I need to keep my promise. Okay, I'll give you this reward if you have a sufficiently good answer. We need to state the rules first, of course. Okay, we are asking how many kinds of lines are there for 4 inputs. So therefore, in terms of boundary that you use to produce those patterns, you can only use straight lines. Use straight lines and produce all the 16 patterns that you claim you can produce, and you get the reward. We have a few people who chose 18. Okay, that's even more creative answer because it's more than 16. And we need to give a bigger reward for that. The bigger reward that I'm going to provide is you can decide anyone's homework grade in this class. Okay, anyone, okay, not just yours. You can, basically you will be the final grader, okay, if you have a correct answer on what you can produce all the 18 kinds, okay, for the 4 inputs that we list here. The deal, okay, 16 kinds. If you have a correct answer, deciding your own grades. 18 kinds. If you have a correct answer, deciding everyone's grade in this class. Okay, so let's see if that's possible by checking some Slido questions for now. See? Okay, let me check. Reset. Okay, first, we didn't see any answers for 16 or 18 yet, but let me answer the questions that are related to the previous part of the class. Okay, the first, sorry. Okay, the first question is, why is the point A corresponding with 0 in the 2D line of f? F is thresholded at 0. Okay, above 0, positive, below 0, negative. And A is a parameter for your hypothesis. So your hypothesis can have a threshold of 0.5, 0.3, 0.01, and so on. So what we're trying to do is to pick a hypothesis that's hopefully close to F. but we don't know f. We only know the examples that we observe on hand. That's the typical learning setup that we're facing. Okay, and here the answer of 7. Okay, and possibly you are talking about the 14 case while we're drawing only 8 here, and you're saying 7 out of 8 can be produced. Okay, and because of the symmetry, you can extend the 7 to 14. So that's similar to the 14 case that many people have talked about, and we will discuss a little bit more later. Does it mean that we can first deal with the input vectors, making sure that they don't degenerate? Okay, so degenerating is an issue when we do an analysis, while in practice, it can be an issue too. Okay, but usually we are not trying to process our data because we want them to fit the theory. We're trying to process our data, we will discuss in future lectures, because we want them to carry some nice properties for the learning algorithm. Okay, so those the practical issues that we're going to face with the actual input vectors is a little bit different from what we will see in the theory now. Okay, but that's a very interesting idea to think about how to process the input vectors that we have on hand first. And here are some discussions about why we are using in the motivating analysis, we are having the 2 epsilon and so on. Okay, and let me quickly explain this again. Okay, so when we talk about xn, the minimum xn greater than 2 epsilon, it actually means because the minimum xn is the one we pick for our g. Right, so we're interested in knowing whether this minimum one is close to 0 or not. If the minimum one is not close to 0, then our G is not close to F. We will suffer from a big E out, where big means E out is greater than epsilon. So we're interested in knowing whether this minimum xn is 2 epsilon away, and this 2 epsilon away comes from the probability assumption. We assume that we're picking things uniformly. So everywhere we have a half density. And when we have a half density multiplied by the 2 epsilon here, we get the E out to be epsilon, which is the error that we're trying to analyze. And my apology that I sometimes forget to switch to the Slido presentation mode, and I'll try to be more careful and when we do the discussion. And how to get this, and as I mentioned, okay, after some derivation, you get that the bad probability that you want to get actually corresponds to having no example falling into the area, the region between 0 and 2 epsilon. Okay, and this 1 minus blah 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 is just to calculating this probability. What's a uniform bound? And I think you mean a union bound. And union bound means we're trying to decompose the probability of a union of events by summing the individual the probability on the individual events. Okay, and thanks for the help on answering. After 5 minutes, there are no people who try to provide their answer on the 16 or nor their answer on the 18. I don't know whether there will be some in my mailbox, but generally I believe that to be perhaps hard. Okay, so hopefully this allows us to convince ourselves that 14 is the best that we can do. Okay, let's revisit the 14 case and see how we did so. Okay, and in the 14 case, we have this pattern that can be achieved by this line, this pattern 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 achieved by this line, and this pattern achieved by this line, this pattern achieved by this line. The only pattern that we cannot achieve by drawing a line to classify the circle and the cross is this guy. Okay, you just cannot do it with a line. or with the terminology we have introduced, you may notice this data set is not linear separable. Okay, when we analyze the perceptron learning algorithm, we mentioned that a data set is linear separable means you can draw a line to separate the circle and the cross cleanly. But this data set is not linear separable, and this data set cannot this pattern cannot be produced by the line. Okay, so that's 7 out of the 8 cases. But because of the symmetry, we can have all the opposite cases, okay, where if we use this, we can produce all crosses and so on. And therefore, that's how we get the 14 by having this guy not possible and all other cases possible. For any 4 inputs, there are at most 14 cases. Actually, I extend my reward to any reordering of the 4 inputs. Okay, you can put the 4 inputs on the 2D plan in any arrangement that you want, but hopefully you can convince yourself that 14 is all you can get. You cannot get 16. That's a very interesting number that we will talk about here. For now, let me name it the effective number of lines. It means the kind of lines, okay, that we try to analyze here. To get the effective number of lines, what we try to do is to consider different numbers of inputs and think about how many patterns lines can produce on those inputs. 1 input, 2 kinds of lines. 2 inputs, 4 kinds of lines. 3 inputs, 8 kinds of lines, or 6 kinds of lines. But we are going to choose the bigger one or the biggest one. So 6 doesn't matter to us. The maximum is 8. And 4 inputs, at most 14 lines. So we're taking the maximum kinds of lines here, and we're going to call it the effective number of lines. And this number must then be less than or equal to 2 to the n. Why is that? That's the number of patterns you can have for big N inputs. That's why I'm placing a super big reward on 18. Okay, 18 is more than 2 to the 4, but it's certainly not possible. And this represents our finite grouping of infinitely many lines. Okay, we have lots and lots of lines here, but we can group them with respect to the number of inputs that we have on hand and count the number of groups, the number of kinds. And our wish is to have this bound that we can plug in effective n to replace our big N. Big N, infinity, we don't like it. Effective N, finite, we may like it. Okay, that's still a question mark. We don't know whether it's possible. But let's think about, okay, if we were really to do so successfully, then we need to at least have something like effective N much less than 2 to the n. Why is that? Remember, in this bound, we're analyzing the bad probability. For the bad probability, we want this to be small. Which part of the bound is small? This part is, sorry, let me use a different color here. This part is small. It's exponentially decreasing. Now, to keep this part small, we need this part to be not too big. Right? Okay, the red part is small, it's multiplied by the orange part, and the orange part should not be too big. Okay, and therefore, we need this effective number to grow slowly with respect of n. Okay, it should be much less than 2 to the n, much smaller than exponential growth, so we can bound this bad probability overall to be small. When we have a small bad probability, we can be confident that our data set is good, then we can do learning. Okay, that's the story we keep emphasizing. So that's the big picture here. Okay, we discussed the effective number of lines. Okay, how can we calculate the effective number of lines? And we want the effective lines eventually to be sufficiently small and be used in the multiple bin Hofding that we have discussed, so we can get some guarantee that learning is possible. Let me quickly see if there are questions on Slido here. Let me do the switching. Okay. What if lines in higher dimensions? Okay, it means x1, x2 up to xn. First, some terminology. Okay, if we're talking about lines in higher dimensions, it's usually called a hyperplane that we will be able to analyze later today or maybe in the next lecture. That's something. And in higher dimensions, okay, we have vectors, x vectors that are multi-dimensional. Okay, and we will also still have multiple x, and we're now interested not in the dimension of x, we're not interested in the number of x. So big N, number of x. If we're going to talk about the dimension of x, we're going to use d, okay, small d to mean the dimension of x, or usually d plus 1 because we're considering an additional dimension of the constant x0. Okay, that's some terminology that we will stick to for our lecture. We have a formula for calculating the effective number of lines. The short answer is yes. The long answer is it's very difficult to compute, and therefore we generally, it's difficult to compute. It's not very difficult to compute. So we generally want to put them in the homework. Yay! Okay, just kidding. Okay, in some previous homeworks of machine learning, we actually asked students to try to derive formula for computing the number of lines. It's a little bit difficult, okay, not too difficult, so you can think about it. But in terms of your question, is there a formula? Yes, there is a formula that calculates the number of lines. Okay, how about nonlinear classification? I think we can separate every point using nonlinear classification. That's a good point. Okay, so actually what we're going to do is to first extend our analysis on lines to any hypothesis set. And then we'll talk about nonlinear hypothesis sets later in the class. Okay, so but basically, although we motivate this analysis by lines, notice that these lines can be extended to this analysis on the number of or the number of kinds of hypotheses can be extended to any hypothesis set that we will encounter. So simply put, n is finite, m is infinite. Infinite lines can be learned in a finite way. We haven't talked about learned yet, but for now, let's say infinite lines can be grouped in a finite way if we just see through a finite number of examples. That's the key of what we're doing here. Okay, m is infinite, but we have a finite number of examples on hand, and therefore we kind of, in the analysis, only need to view through those finite number of examples, and therefore we only need to consider a finite number of grouping. Okay, that's the key idea. Not as simple as it sounds, actually. Okay, the main proof is very difficult, but the key idea is we don't need to consider infinite number of hypotheses. We can group them by the finite number of inputs, okay, that we need for our analysis to work. Oh, sorry, I seem to have accidentally hidden a Okay, that's here. If x is nonlinear, can we change x's that we view, meaning change to linear and so on? Okay, thank you for the very interesting idea. It will be one of the ideas that we're going to talk about maybe a week or two later. Okay, great. Let's continue with the lecture. Okay, so now, extending from lines to arbitrary hypotheses. Remember, we have a hypothesis set in our learning setup. Okay, and hypothesis set contains hypotheses, and we will, for now, consider only binary classification hypothesis where we're mapping an input space to cross or circle, binary only. You'll ask, how about multi-class? How about regression? How about multi-label? Blah, blah, blah. Well, you can do similar analysis. You can do those analysis one by one and so on. And also there are ways to connect those problems to binary classification. But we will not have time to encounter all of them in this class. We will talk about binary classification first to let you understand the essence. And then when we evaluate a hypothesis on a finite number of input vectors, we call that a dichotomy. Okay, so dichotomy is the pattern that we produce on those finite number. So this is what we did in the previous lecture, where our hypotheses were lines and our inputs were those drawn on the screen for you. But you can apply this concept to any hypothesis set. So after applying the hypothesis on a finite number of lines, you get a pattern, which is basically a binary vector. The binary vector is of length n, where n is the number of examples that you have on hand. So this is similar to your hypothesis, but now it's limited to the eyes of those examples. Again, what we mean by 以管窥天. Then what we do? Okay, we apply the whole hypothesis, all the hypotheses on the hypothesis set to in the hypothesis set to all those inputs. Then we can get all possible dichotomies implemented by the hypothesis set on those examples. That's what we did by drawing different lines, right? Okay, this line, this dichotomy, that line, that dichotomy. So maybe on line 1, we get a dichotomy, something like this. Line 2, like this. Line 3, like this. And line 4, blah, blah, blah. And there may be repeated dichotomies. For example, maybe this dichotomy is repeated by some other hypothesis. This dichotomy is repeated by some hypothesis. And when I write this notation, applying a hypothesis set on this, we mean we gather all these dichotomies, remove the duplicates. We need the unique one, so I can add unique here. So we have a set of possible dichotomies, and then what we do is to try to bound the size of this set. Now, for the hypothesis sets, we have, for example, all lines, which is of possibly infinite size. When restricting to a finite number of inputs, our sets are just binary vectors, and there are at most 2 to the n different binary vectors, and therefore the size of dichotomies, the dichotomy set is upper bounded by 2 to the n. And this is our candidate. Okay, the size of this set is our candidate for replacing big N. Big N, infinity, this size possibly finite. Now, this value depends on the inputs. Okay, for example, as we see, when we have inputs like this, and our hypothesis set contains lines, then this size is 8. If I have inputs like this, and the size is 6. Now this makes it difficult, okay, for the analysis, okay, because sometimes you need to consider 8, sometimes you need to consider 6, and so on. It's just too difficult. And what we're going to do, okay, given that if we use this value to replace big N, then this value represents something bad. Okay, so let's try to consider the worst case, okay, where the value is as bad as possible or as big as possible. Okay, so the worst value that this size can be is the maximum here. So we are going to take the maximum of all possible things. So basically, all possible sizes. Basically, what we do is we can arrange the inputs arbitrarily. Okay, you want to put them as a triangle, collinear, whatever, or even put them at the same place. It's your call. But after putting the inputs, you calculate the number of dichotomies that can be implemented, compute the size, and do all the possible arrangement, take the maximum. That's the value that we care about, that I'm going to call it little n h. Okay, and the effective number of lines that we see previously is just a special case where our h is taken as lines. But in the future, we will have hypothesis sets that do not contain lines, and we can still use this analysis. Okay, this analysis tells us arrange your input in whatever way you want, compute those dichotomies that can be produced by your hypothesis set, compute the size, take the maximum. That's the effective number that we care about. Okay, and this makes things easier. Okay, moving from the actual size to an upper bound. Okay, the maximum value is an upper bound, gives us the flexibility of doing analysis. So for example, if we look at lines in 2D, we're not very familiar with that now. 2 for size 1, 4 for size 2, 8 for size 3 examples, simply because it can be 8, can be 6, can be other numbers, but 8 is the maximum. But for 4 inputs, okay, we have worked hard to ensure that only 14 is possible. And we call this the growth function. Okay, it measures how the kind of hypothesis grows as the number of examples grow. And what do we want the growth function to be? Okay, it has some very good properties that we care about. For example, it's upper bounded by 2 to the n and therefore is finite. And we want the growth function eventually to grow slowly. If it grows slowly, the back probability grows slowly as well. Let's look at some concrete cases of the growth function. Let's first revisit the motivating example that we had. In the motivating example, what we did was say, on the number line, on the real line, okay, we have hypothesis, okay, that tries to say the bigger ones are circles, the smaller ones are cross with respect to a threshold that we call A. Okay, and we're generalizing it a bit. Okay, we are talking about the whole real line. Okay, instead of just a small part of the real line. Now, consider our hypothesis set. Okay, which contains all possible HA. Okay, so each HA just says, okay, I'm going to use the threshold to decide which part is circle, which part is cross. Now, how many patterns can we produce? Okay, how many different dichotomies can we produce with this hypothesis set? Let's see. If we have, let's say, 4 examples, let me draw another line. Example 1, example 2, example 3, example 4. We have 4 examples. Now, the question is, can we produce circle, 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 circle? You say, aha, it's easy. We can produce it by setting A here. And then we can get circle, 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 circle. How about can we produce circle, 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 cross? Aha, easy. You can say, let's put the threshold here, and we can produce this pattern. Okay, something more interesting. Can we produce cross, cross, circle, circle? And no, you cannot find a hypothesis that produce this, because all our hypotheses need to have right-hand side being a circle and left-hand side being cross. So this is not possible. And how about another one? Okay, can we produce circle, cross, circle, cross? And you cannot produce that. You need to have all the right-hand side being circle, all the left-hand side being cross, and therefore, no. So let's list, all the possible patterns that can be produced by this hypothesis set. And what we will see is that those are the only patterns you can get on 4 inputs. I'm listing them here. All the 5 patterns are here. Okay, one dichotomy if you put the threshold in between any of the 2 consecutive examples. So n inputs, at most n plus 1 dichotomies. Okay, so that's a growth function. Now we can analyze. We have a hypothesis set. We introduced the hypothesis set in the very beginning of this class, saying this is the motivating example we're going to analyze, and we find that its growth function can be very simply computed. Actually, if you're interested, this is just a sum of the 1D perceptrons. This is called the positive half of 1D perceptrons. And you can say there's a negative half. That says a threshold with a different sign and so on. But we are only considering the positive half here, and the positive half gives us 5 different dichotomies, at most 5. And the growth function mh of n is n plus 1. Little n because it's smaller than big N. H means with respect to the hypothesis set. N means we're considering big N input. For example, in here, we have 4 inputs, and we're calculating the maximum number of possible dichotomies. So this is interesting because we actually see this N plus 1 is much smaller than 2 to the N, especially when big N is large. That gives us some hope. If in this case, we can use n plus 1 to replace big N in the bound, maybe we can get some learning guarantee. Positive interval. A positive interval also works in a one-dimensional space, and in this particular one-dimensional space, what it tries to do is to have 2 thresholds, L and R. Within the range of the 2 thresholds, it's positive 1. Outside of the range, it's negative 1. Question now, if we consider this hypothesis set where your flexibility is to vary all the different kinds of threshold combinations, what are the patterns you can get? So you need to have the middle range being circle and the outside range being cross. And these are the possible patterns that we list. And you see, it seems rather complicated and so on, but you should learn from your combinatorics class that to calculate this number, all you need to do is to choose the left threshold in one region, the right threshold in another region, out of the 5 regions that we're considering here. So place your threshold in any of the region, the 2 threshold in any of the 2 different spots. So then you can produce a dichotomy. For example, this is a particular dichotomy where you put L here and put R here. So there's 5 choose 2, or more generally, n plus 1 choose 2. So you can basically decide which part to be positive. And you have another plus 1 indicating the all negative pattern here. So this is just a very simple math that you will encounter in your typical combinatorics class. And this value results in a polynomial here that's also much less than 2 to the n, when n is large. So that can be good news. Okay, if we have a growth function that's grows much slower than 2 to the n, then it can be useful in the bound that we want to consider. Okay, I'm going to introduce another hypothesis set, which is not really useful, but just to mathematically tell you that there are some growth function that can grow really fast, meaning similar to the n. And I'm going to call this function, some of you described nonlinear classification in your questions, and actually this corresponds to nonlinear classification within the 2D space. Okay, so let's consider examples in the 2D space. And we're going to do classification with convex sets. In Chinese, 凸集合. So think about your classification boundary is convex, 凸凸的. Okay, 如果你真的很难想象的话，想象凸多边形. Okay, if it's really hard for you to imagine, you don't need to imagine convex set. You just imagine convex polygons. And within the convex polygon, we have a blue region. Okay, so everything inside is blue, everything outside is red. Okay, now let's consider a hypothesis set that contains all those convex boundaries as our hypothesis. Now, what's the growth function of this hypothesis set? Let's see. Growth function means we need to arrange our input points in arbitrary ways, calculate how many patterns we can implement, and then compute the maximum value. Now, instead of arranging the inputs in arbitrary way, I'm going to arrange the inputs in a very special way that results in the worst case. What's the special way that we're going to consider? I'm going to arrange the inputs on a big circle. Okay, so basically, I'm trying to spread the input out in some way. Now, let's say we have inputs, okay, like these points in a 2D space. And then, what do? We want to check if a pattern can be implemented. We want to check if a dichotomy can be implemented. So what we do is to check, okay, let's say, a pattern that we want to implement. For example, let's say we want to implement circles here and cross here. Can we implement this pattern, this dichotomy, with a convex set or with a convex polygon? Yes. What do? We link all those points together as a polygon, enlarge the polygon a little bit such that it covers the positive points within, and just a little bit so we won't be able to touch any of the negative points. And this polygon, this convex polygon, implements the dichotomy that we want. So a dichotomy, a polygon can implement. A dichotomy, a polygon can implement. A dichotomy, a polygon can implement. For any dichotomy you can think about for those inputs on the bigger circle, we can implement it with a convex polygon. And therefore, it means our h of x1, x2, blah, 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 xn on this very special arrangement of those x contains all dichotomies. All dichotomies means the size is 2 to the n. 2 to the n is the worst case for a size of dichotomy, and therefore the growth function is 2 to the n. We're showing this. Okay, I have to be very honest here. Okay, this has no actual value in terms of machine learning, not at all. But we're just trying to tell you that in theory, there can be hypothesis sets that grow as fast as 2 to the n, and that's not good for our theoretical analysis. We're interested in the good hypothesis sets, like the previous two that we talked about, where the growth is somewhat slow. Okay, that's the point of introducing this particular hypothesis set. Okay, we just say there are some hypothesis sets like this that can keep producing all dichotomies, and we don't like it. When this happens for some particular n, we call that H shattered the hypothesis set. Okay, and shatter means actually something more like conquered, okay, or producing all possibility. This is just a name that people traditionally use to describe this phenomenon. On those particular endpoints, we produce all dichotomies on those n inputs such that the dichotomy set size is 2 to the n, and this is called shatter. Okay, we will encounter this in some future analysis. So if we encounter the growth function to be 2 to the n, then there are some n inputs that can be shattered. Some of them, some arrangement, okay, not all arrangement, okay, but some arrangement. For example, we know that NH of 3 equal to 8, where this H are lines in 2D. We know this, and this means there exist 3 inputs arranged in a very special way that I draw here that can be shattered 8 dichotomies. Okay, that's the notation, or that's the definition we are going to use a lot in future proofs. Okay, so you better keep this in mind now. When you see a growth function that reaches the worst case of 2 to the n, it means there exists n inputs that can be shattered. Now, we encountered 4 growth functions so far: mh, n plus 1 for positive rates, for positive intervals, second order polynomial. For convex sets, always 2 to the n. For 2D perceptrons, sometimes 2 to the n. Sometimes less than 2 to the n. Some cases, meaning n equal to 4, okay, to what we have examined so far. Now, what if this little n replaces big N? Remember, we put a question mark here, but let's say what if? Exponential is bad because we cannot get any guarantee on the right-hand side. If little m is exponential growth, like 2 to the n, and we're doomed. But if this is polynomial, then with this term that's exponentially decaying, then it's good. It actually means if we get bigger and bigger and bigger and bigger n, okay, where n is the number of examples, we can decrease the bad probability to nearly 0. Then learning is possible. So the question we want to ask is, for 2D perceptrons or general perceptrons, is mh, is the growth function polynomial or not? To analyze this, let's first see when the growth function would be not 2 to the n. Okay, for 2D perceptrons, let's look at it. 3 inputs, 2 to the n. There exists something, some input arrangement that can be shattered. 4 inputs, no shatter. So 4 inputs is the first number of examples that we see hope. In Chinese, we call it 一线曙光. we see hope, okay, much like in Star Wars, okay, A New Hope, okay, we see hope somewhere for us to achieve something less than, or hopefully much less than 2 to the n. That's on 4 inputs. We call this 4 here the breakpoint. Okay, so basically we see hope in these breakpoints because they satisfy MH to be less than 2 to the k. Okay, so let's see for perceptrons, the breakpoints that we find, breakpoints at 4. If we have a breakpoint at 4, then we should also have breakpoint at 5, at 6, at 7, and so on. Why is that? Because breakpoint tells you you cannot produce every dichotomy. If on 4 inputs you cannot produce every dichotomy, on 5 inputs you cannot produce every dichotomy. Otherwise, if on 5 inputs, if you use a contradiction proof, if you can produce all dichotomies on 5 inputs, then hiding one of the input vectors, you can produce all dichotomy on 4 inputs. But this is not possible. So a breakpoint means all other future points are breakpoints as well. And therefore, we're very interested in the minimum breakpoint k, which is 4 for 2D perceptron. Now, minimum breakpoint of 2D perceptron will be 4. And by minimum breakpoint, we can do some analysis, and that reaches interesting result. But first, let's look at the minimum breakpoint for positive ray. The growth function for positive ray is big N plus 1. So when n equal to 1, the growth function is 2. N equal to 2, 3. Breakpoint, yay! Right? Because 3 is less than 4. So the breakpoint for positive ray, the minimum breakpoint for positive ray is 2. How about positive intervals? Okay, I won't go into the details. You can do the computation by yourself, and you can see that the minimum breakpoint for positive intervals is 3. So we can continue the process, and if the growth function is always 2 to the n, there's no breakpoint. And for 2D perceptrons, we know its minimum breakpoint is 4 by our analysis. And here comes the beauty of skipping the theory. Now, there's a 2-hour proof that we can teach about what happens after we know the breakpoint and how we get the theory behind generalization and so on. But that's very, very challenging. And in my opinion, not necessary for everyone. So we will skip those theorems in the lectures. We will not have problems related to those in the homework. Yay! But we encourage the mathematically inclined students and maybe computer science students to check the proof, because the proof applies many properties from combinatorics and statistics to actually come up with the final theorem. Okay, you can check the proof in Mandarin in our earlier MOOC. That's one possibility. You can check the proof in the Learning from Data book. Okay, that's another possibility. But anyway, after we get to the proof, okay, if you check it, we will basically be able to separate the growth function to 2 possibilities. One growth function without any breakpoints, where the growth function keeps being polynomial, being exponential. That's for sure. Okay, that's by definition of having no breakpoint. But once the growth function has a breakpoint k, once it has a minimum breakpoint, then we can prove that the growth function grows polynomially, slowly. Okay, if you don't know what it means to be growing polynomial, slowly. And this slowness is roughly in the order of big N to the k minus 1, where k is the minimum breakpoints. Okay, that's the theory we want to go into in class, but that's an interesting result. It basically says the good hypothesis set should have a minimum breakpoint. If we have a minimum breakpoint, we plug it into the Hoeffding's inequality, we get the bound, we can guarantee E in and E out are close, we get E in low, we get E out low, done. Okay, so good hypothesis sets should have a breakpoint. Okay, we are not touching the theory, but I'm hoping that you get this message. Okay, finally, some time for questions. Because it is very close to our break time, let's take a break first so we can allow everyone more time inputting the questions, and I'll answer them in the beginning after the 10-minute break. Okay, so let's take a 10-minute break for now. Okay, great. Welcome back. Okay, let me check the Slido questions for now. Okay, is it hard to find a good hypothesis in set H even when we know the breakpoints? Yes and no. Okay. Yes, it's not touched yet in this part of the lecture. And as we mentioned, the good hypothesis, okay, if we think about it, means you need to do a certain optimization within the hypothesis set. Okay, and we haven't talked about optimization yet. Okay, so it may seem hard now. But no, it may not be that hard because it's just optimization. Okay, it's on the data that you can control, and therefore, if we establish the connection between E in and E out, then minimizing E in is generally not as hard as it looks like. Okay, can we make sure that the hypothesis that implements the same dichotomy have similar E out so the union bound can be reduced? And this is exactly what we're trying to do here. Okay, basically, by grouping the hypotheses together, we are kind of ensuring that they have similar E in or the same E in, right? Okay, because hypothesis in the same group produces the same dichotomy on the pattern on the inputs that we're interested in. So their E in are the same. But the tricky part is how to guarantee that they have similar E out. And this is not trivial and requires lots of mathematical efforts to prove. Okay, but the idea is that we can try to do some more fine-grained grouping, okay, beyond the examples that we have on hand, so that we can guarantee hypotheses in the same group have similar E in and similar E out. Okay, that's basically what's done in the theoretical proof. We won't be able to touch the details of the theoretical proof in the lecture, but I hope you understand the high-level idea of it. Why can this is a very good question actually. Why can we not have the growth function to 2 to the n? If we look at it, if we put 2 to the n and then multiply by the exponential minus n, we can still get this to go to 0 when n goes to infinity, and this is simply because E, okay, the exponential value is actually greater than 2. Okay, so the limit of this still goes to 0. Yes, but if you recall, in the bound that we intend to use, it's not E to the negative n. It's E times 2 epsilon, negative 2 epsilon squared to and then multiply by n. And typically, what's epsilon? The epsilon that we're thinking about here is small, because epsilon is what we use to measure the difference between E in and E out. Okay, so while 2 to the n multiply exponential negative n goes to 0. If we plug in a small constant here, which in this case 2 epsilon squared, that's small, then most likely this whole guy grows as big N grows. Okay, so that's why we are more interested in this guy not being 2 to the n, because 2 to the n, it would tell us that, okay, the bound, even if it works with super big epsilon. And super big epsilon is not interesting to us because big epsilon means in and ER are far away. We're not interested in that. We're interested in and ER being close, epsilon being small. When epsilon is small, this is an exponentially decreasing term that decreases somewhat slowly, not super fast. It's exponential, but not super fast because epsilon is small. And therefore, we want something to grow even slower. We want the MH here, the little MH here, to grow even slower. Okay, that's why we want it to grow polynomially, okay, not exponentially, not 2 to the n. Pi 4 is the limit of breakpoint, and what does breakpoint mean? Okay, so as we mentioned here, okay, breakpoint is what we use to analyze the growth function. If we cannot find any inputs that can be shattered by the hypothesis set, we call it a breakpoint. Or more formally speaking, it's just this. A breakpoint needs to satisfy this. The growth function evaluated on the breakpoint is less than 2 to the k. So take the 2D perceptron. 2D perceptron, remember, n equal to 1, n mh of n equal to 1, growth function 2, n equal to 2, growth function 4, n equal to 3, growth function 8, n equal to 4, growth function 14. Yay! That's the breakpoint. Why is it not 8? Because when there are 3 points, there can be 8 dichotomies, there can be 6 dichotomies, and so on. We are taking the worst case. Worst case is 8. And the worst case is 8, which is still 2 to the n. We don't call it breakpoint. Okay, it can still be shattered by some inputs. The some inputs we're talking about here, 3 points arranged in a triangle. So it's not a breakpoint. Only if we are absolutely sure that 2 to the n is not achievable, we call it a breakpoint. So in this case, it's definitely not 16. 16, no, definitely not. We call it a breakpoint. Okay? When 2 to the n is still possible, we don't call it a breakpoint. That's the definition that we're using here, and that answers these 2 questions, 3 questions actually, on Slido. And shatter means, okay, we defined shatter in the previous slide, I think, okay, sorry, a little bit before here. Shatter means 2 to the n. Okay, so we introduced several different names here. Shatter, 2 to the n. You get some inputs, you see 2 to the n, shatter. You get every input, you don't see 2 to the n, breakpoint. Let me repeat. You get some inputs, okay, and then you don't see, you see 2 to the n, shatter. Get some inputs, you see 2 to the n, shatter. You get every possible input combination, you don't see 2 to the n, breakpoint. That's the basic definition that we have, that we will use in our next classes. And we talk about convex sets. Okay, we talk about convex sets as a hypothesis. How about non-convex? Let me try to say the following. Non-convex sets, as you can imagine, are generally more flexible than convex sets. Okay, non-convex sets means you can kind of draw arbitrary boundaries, okay, on your plane. That's more flexible. And when a hypothesis set is more flexible, it can easily produce different kinds of patterns, okay, by moving in multiple shape, or in Chinese, 变形虫. So if you have a boundary, okay, that can be kind of arbitrary, much like the strike zone of 中华职棒, okay, the CPBL, okay. If you watch baseball, some people claim that the strike zone in CPBL is like an arbitrary shape, okay, not really rigorously defined and so on. Then it's flexible. Then you can use it to arbitrarily decide whether a ball is whether a pitch is a strike or not. Okay, then that's problematic, right? Okay, then you have much flexibility, or then you can easily reach 2 to the n. Okay, you can easily have a growth function that's 2 to the n. So that's the short answer to your question. Okay, so I don't know, this joke is so hilarious, so I really want to repeat it with Mandarin. OK， 所以这里的问题就是，如果我们用的不是 convex set 做 hypothesis， 而用的是 non-convex set 会怎么样？然后我的回答就是 non-convex set 就是像那个变形虫的形状一样，你有很大的自由度，然后做任何形状。那变形虫的形状就像中华职棒的好球带一样，如果你有在看棒球的话，那如果像那个好球带一样的话，你就可以任意的判定一个球是好球或坏球，也就是你可以任意的 generate 任何你想要的 dichotomy， 那么你的成长函数，你的 growth function 就很容易跑到 2 to the n。那这是我的回答。Okay, thank you for bearing with me on some Mandarin explanation on a joke that I thought about on the spot about the shape. And thank you for the question that inspires this interesting joke here. Sometimes I need to prove that I'm still able to speak Mandarin in some sense. Okay, so bearing with me and on explaining some of those concepts, especially jokes in Mandarin. Okay, so people are asking whether the non-convex growth function is greater than or equal to convex growth function. This is a tricky business, okay, but if you look at the proof that we have, actually, I think both of them would reach the upper bound, which is 2 to the n. So convex hypothesis set has grown into the worst case. Right, and non-convex, okay, is also bad, and both of them grow to the worst case. So it's not really greater than or equal to, but it's more that like equal to in terms of the growth function. Okay, thank you. And so there's a question here: if we cannot correctly fit each data into the right region, not shatter, we'll have a better upper bound. Okay, that's the one of the philosophical issues that we're going to discuss. Okay, we are currently highlighting that we cannot produce every possible dichotomy in order to get a bound on the bad probability. That's what we're motivating here. But think about this, okay? If you cannot get every dichotomy, it actually means for some possible label patterns that you're interested in, you cannot get E in equal to 0. Okay, so that's the two sides of the explanation, you know. Okay, we're saying for bad probability, we don't want our hypothesis set to be too complicated, and therefore we want it to have polynomial growth function, for example. But if it only has polynomial growth functions, it must mean its power is somewhat restricted. And we will discuss about the philosophical debate later when we finish all the theoretical parts. If we apply some feature transformation, it seems we can find a line to separate cross and circle that are not separable before. Yes, okay, that's a very good hint that we will go into later to discuss future hypotheses where we have nonlinear boundaries. Okay, great. Thanks for the many inspiring questions, including the one that motivated me to tell a joke in class. Okay, actually, something that I really miss teaching in actual classrooms is that in actual classrooms, it's much easier to think about jokes to teach. Also, in Mandarin, it's kind of easier for me because Mandarin is the earlier language that I learned, so it's easier for me to come up with jokes for Mandarin teaching. But for English teaching, I can still try, okay? But it takes some efforts. Okay, so what's the bad bound that we can get? Remember, this is kind of our motivation. We want a bad bound. Okay, that's something like this. So I'm stating the bad bound in its original form, okay, where we're stating we're interested in knowing whether there's one of the hypotheses that's bad. Okay, that's the formal statement of the bad bound. And originally we say let's use little mh to replace our original big M, and then the bound should look like this. The actual bound that researchers can prove is like this. It's similar. but coming with some other constants, as you see here. For example, there's the 1/16 here, there's the 2 here, there's another 2 within big M of H, and so on. And this bound needs n to be large enough, meaning n is lower bounded by some value, and so on. Again, we're not going into the details of the proof. Okay, the detail of the proof is very technical and takes a lot of time, while bringing us some insight but not a lot of insight. Okay, so I'd rather just tell you the result of the proof, tell you that it's similar in shape to what we want, okay, but not going into the details. If you are mathematically oriented and want to know the details, go to our earlier MOOC for a Mandarin explanation of some key ideas within the proof, and go to the Learning from Data book for the detailed steps. Okay, that's the bounds that we're able to get. The only thing I'm going to explain a little bit here is this MH of 2n. Not n, but 2n. It is actually stating the difficulty that we had with one of the questions you're asking. Remember, we're grouping the hypothesis by kind, right? By their performance on n examples. But if we only look at n examples, the n input vectors that we have on hand, we cannot get the bound because on those n examples, E in similar for the hypothesis within the same group, but E out can be different. We have no guarantee on the E out. Okay, E out can fly anywhere, just like what we had in the invisibility of learning part. So by only doing grouping on n examples, we can at best guarantee E in to be similar, but no guarantee on E out. How do we get a guarantee on E out? We get a guarantee by requesting God to give us a few more examples. And the a few more that we take in the bound is n more examples. By requesting for n more examples and then do the grouping, we can have some guarantee that E in and E out can be close to each other by using m of them to evaluate E in and m of them to pin down E out. Okay, so that's the key idea within the proof. I'm not going into the detail here, but I think it's worth mentioning why we have 2n instead of n. Okay, that's the difficulty of the proof here. If we only do grouping on n examples, no, we cannot get the bound. If we do grouping on more examples, okay, here n more examples, then we're able to get the bound by trying to ensure that within the same group, the group comes from looking through the eyes of 2n examples, E in and E out would be most likely similar. And this bound are derived by two statisticians, and is generally called Vapnik-Shermaninkis bound. Okay, that's the first name of the last name of the two statisticians. And as you can see, that's how machine learning, or at least the statistical machine learning we talk about, connects closely with statistics. Okay, this is like extending the statistics you learned in your statistics 101 class about Hopkins inequality all the way to complicated learning scenarios where you have an infinite size of hypothesis to analyze. And through the infinite sized hypothesis, we get its characteristic in the growth function that we define, and use this particular growth function, plug its particular growth function into the Hopkins inequality to get the bound that tells us the bad probability can be small if this is polynomial and this and is big enough such that this term is super small. When is this guy polynomial? When we have a break point. Okay, so having a breakpoint for the growth function is then very important for this bound to work. Before we go into more variations of the bound, let's talk about the interpretation of this. The interpretation is that if we are able to get this bound, okay, not if, okay, I mean through the formal proof we're able to get this bound, then it tells us you have a hypothesis set and statistical large D. Statistical large D means IID sampled from an unknown distribution of interest. Then we have this bound which tells us that you can do any algorithmic selection within the hypothesis set. As long as your algorithm picks something from the hypothesis set, because G is one of the hypotheses, it's guaranteed to be safer than the bad case that we analyze. So this is the bad case we analyze, and this is one of the hypotheses we eventually select by our algorithm. And there's this bounding, okay, that was the question asked from one of the students saying, okay, so then we can have a guarantee for the final G that we select. And we need this D to be large enough. What's large enough? Well, there are some technical details in the bound, but basically it says your N should be large. Okay, then when you have this bound, if there's a breakpoint, then what happens is that you can replace this growth function with an upper bound, okay, that's of this form. Okay, this is a polynomial, okay, with the order of k minus 1, basically. Okay, and we're ignoring the details of the proof here, and this orange part requires some assumptions. Okay, requires our breakpoint to be larger than or equal to 3, requires n to be greater than or equal to 2. I'm crossing this out simply because we already assumed our data set to be large enough, and so on. So polynomial here, and exponentially decreasing here, eventually the bad probability will be upper bounded, and therefore the risk of getting a bad G is upper bounded as well. So this is what learning does. We need a good hypothesis set that comes with a breakpoint, and we need a good data set that's large enough. Then we can guarantee good generalization between E out and E in. Then we need an algorithm to pick a hypothesis with a small E in. That's good algorithm, hopefully. Then we can say we have learned. That's the learning step. But those learning steps are not deterministic. Why is that? Because even if we have a good hypothesis set, even if we have a good data set, and here good means large enough, we need another level of good where we need good luck to get a representative hypothesis set. So this good D need not just large, but also lucky. Okay, so if we're lucky enough, we can say we probably generalize, and therefore we probably learned. So that's the component of learning, and now you see clearly why we're separating these three in the learning flow. Good hypothesis set, we need to analyze, or we want to analyze whether it has a breakpoint. A good data set, so size matters. Okay, we need to analyze whether it's of sufficient size, or we will talk about the meaning of sufficient size later with respect to the hypothesis sets that we have on hand. And not just good size, but we need to have a little bit belief on good luck. Okay, so once we get a data set that's sufficiently large, with good luck, we can say the data set is representative for every hypothesis in the hypothesis set. Then we ask a good algorithm, an optimization algorithm, to give us a G with small e in. That's the interpretation of the VC bound. And accompanying the VC bound, there's a formal definition called the VC dimension. And VC dimension is, okay, we're introducing many different names here. We're introducing shatter, we're introducing breakpoint, we're introducing growth function, and so on. I bet you're a little bit confused, but just bear with me with one more, because we will use VC dimension throughout the class. Okay, so this dimension is arguably much more important than all the previous definitions that we have. VC dimension is just a formal name of breakpoints, except that it's for non-breakpoints. Remember, we say we're interested in the minimum breakpoints. If we take the minimum breakpoint and then decrease it by 1, we get the maximum non-breakpoint. And that's called the VC dimension. So what do we have? 2D perceptron. Remember, n equal to 1, 2 patterns, n equal to 2, 4 patterns, 4 dichotomies, n equal to 3, 8 dichotomies, n equal to 4, 14 dichotomies. We say this is a breakpoint, and this is VC dimension. Just one less. Okay, and VC dimension of a hypothesis set can be viewed as a property of the hypothesis set. It's the largest number, large number of examples where we can achieve shattering. So shattering, VC dimension. And then no shattering, breakpoint. Okay, when we are saying shattering, we're saying there exists a data set that can be shattered, VC dimension. Okay, there exists, of course, the maximum number that there exists. When there are, for all data sets, no shattering, breakpoint. Okay, or the minimum one, minimum breakpoint. Okay, so that's the definition we have. And if you're not familiar with the definition, I strongly encourage you to go back, review the lectures we have today, and make sure you know them. Because next time we will prove a very important theorem with those definitions, trying to highlight the VC dimension of, trying to pin down the VC dimension of arbitrary perceptrons, not just 2D perceptron, 3D, 4D, 5D, 6D, 112, 6D, whatever perceptron, we're going to prove what their VC dimension is. So if we have the number of examples that are fewer than the VC dimension, then H can shatter some big N inputs. If N is bigger than the VC dimension, then it's guaranteed to be a breakpoint. Okay, you cannot shatter any such an inputs. And just to for notation, okay, we when we say breakpoint, we will commonly use K. Okay, simply because it makes it easier for you to imagine that this little k is talking about breakpoint. And if you followed, okay, what we said we're not going to prove with the combinatorial quantity and so on, you will eventually be able to derive a very simple bound, okay, that says the growth function is less than or equal to n to the VC dimension. Remember previously we say it's big O of n k minus 1. Now we're pinning it down to O of not just big O of n k minus 1, but n to the VC dimension that we call dVC here. VC dimension is smaller than breakpoint, so it already captures the k minus 1 part. And if we put a little bit more assumptions here, we can remove the big O and directly use n to the dVC as a cleaner upper bound. Okay, we're familiar with the breakpoint, so I'm just reiterating their VC dimensions here. Positive ray, breakpoint, 2. VC dimension, 1. Positive interval, breakpoint, 3. VC dimension, 2. Convex set, breakpoint, no. VC dimension, infinity. 2D perceptrons, breakpoint, 4. VC dimension, 3. And I'm showing here the patterns that can be shattered. Right? When we say VC dimension equal to 3, we need to find some inputs that can be shattered. So these are the inputs that can be shattered by convex intervals. These are the inputs that one input that can be shattered by positive rays. And anything can be shattered by convex sets. And that's why the VC dimension is infinity. So for us, good hypothesis set means finite VC dimension. Okay, that's the important message that we want to tell you today. Finite VC dimension, it means our G, the G selected by our learning algorithm, can generalize if we have a data set that's large enough. This is regardless of what learning algorithm you use. You can use a learning algorithm that selects the minimum E in. You can use a learning algorithm that randomly selects a hypothesis. You can use a learning algorithm that selects a maximum E in hypothesis. It doesn't matter. In terms of generalization, whether E in is close to E out, VC dimension, VC bound tells us that as long as you have a finite VC dimension, the algorithm will generalize if you have enough examples. This is regardless of the input distribution P, much like Hofstad's inequality, and regardless of the target function. So we don't need to know that. We just need to know there is this guarantee. And therefore, that gives our focus really to the data set, in particular, whether we have enough examples. Okay, that's big N here. And the hypothesis set, okay, which is really if we have a breakpoint or if we have finite VC dimension. And this provides the worst guarantee on generalization. It is regardless of what your algorithm is doing, what probability you are using, what F you are using, you can have anything in there and generalization is still guaranteed if N large enough and you have a finite VC dimension. That's the message behind the VC bound. Okay, now the VC bound that we told you is the noiseless VC bound. Basically, it says we have an F there. Remember, we have an F. We use that particular F to measure whether it's the same as H or not. We use the bin model to color as orange and green and so on. In the main proof of the VC bound, actually things are similar. Okay, you imagine you have marbles that needs to be colored according to the difference between F and H, and you have multiple bins that you want to analyze and so on. Because we have a fixed F and we're just measuring the difference between this fixed F and H, okay, we can say that this is a case that doesn't consider much noise in learning. But real-world learning problems can be noisy. For example, in the credit approval example that we discussed, we can have noise in two parts. One part is noise in Y. For example, this is a good customer, but for whatever reason, maybe dataset error and so on, the customer was mislabeled as a bad one. That's called noise in Y, okay, in the label part. And it's denoted as, for example, this particular case where we have a cross that seems to be closer to circle case or and so on. We don't know exactly whether it's a noise, okay, but we can kind of explain that it's a possible noise, okay, because of mislabeling or something. And this can be covered by a distribution, let me call it P of Y given X, which says for an X, there's some possibility that we're getting an F of X, a determined answer, but some probability that we're getting a noisy answer that's different from F of X and so on. Okay? So think of this uncertainty in terms of label noise being governed by a distribution. Of course, you can also have noise in the input as well, such as errors in filling in the application form and so on. But that's generally discussed in the distribution on X, the input part. Remember, in the bin model, we can have a distribution on the marbles. You don't need to sample the marbles always uniformly. Often still holds as long as you are sampling ID from the distribution. Similarly, the input noise can be governed by a distribution. Okay, that's just placing weights or probability mass on different marbles and so on. So there are two kinds of noise. We already know how to handle this in the VC bound, in a sense, okay, by having marbles picked with uneven probability and so on. You can trust that halving still holds and for estimating the average and so on. And the next message I'm going to tell you is that VC still holds when we have noise in Y. As long as we do the analysis all over again with a different kinds of marble. The key behind VC bound is the marbles. Originally, we do marble sampling, and then we have a deterministic color by f of x. Now, imagine you have a different kind of marble, where you still do marble sampling with p of x, but it has a probabilistic color that keeps changing. Okay, much like the particles you see in quantum physics or something. Okay, it has a probability of having one spin value and probably of having another spin value and so on. Okay, so basically, you have some properties there that is probabilistically changing, okay, until you observe it or something. Then, although the color of each marble keeps changing with respect to some probability distribution, as long as we sample from the bin IID with respect to the two distributions, P of x and P of y given x, and then kind of recording the y we saw immediately after sampling, then we can still get an estimate of probability of orange at any timestamp within the marble. So we can still get an orange portion, the estimate to the orange portion, even if we have noisy marbles. That's how things work, okay, to extend VC to probabilistic marbles or the noisy learning scenario. Basically, it says VC holds if we sample ID for the marbles, the inputs, and we sample ID for the color or the label that's used for coloring. And this can be actually combined to a case where we are doing ID sampling from the joint distribution between input and output. That gives us the new learning flow that where the main corrected part is now we're able to accommodate noise. We no longer assume that our label comes from a clean target function. We assume our label comes from a target distribution that can be unknown. Okay, and this target distribution governs the original target function plus some possible noise. As long as we're generating those labels ID from the distribution and use the same generation process to do the evaluation, VC tells us that this whole part above can remain unknown while we can do the learning flow at the bottom to get a hypothesis where E out is close to E in. VC still works under those noise settings. Okay, so that's what we want to tell you about the VC bound, okay, including the VC dimension and quickly extending the VC bound to noisy case or trying to convince you that it still covers the noisy case in some sense. We have a few minutes. Hopefully I'm able to get into the Slido questions before we conclude here. How do 1/16 and 1/8, these two numbers in exponential come out? It's really technical detail. Okay, and unfortunately, we're not able to explain them in this class for sure. If you are super interested, go to the Learning from Data book for the details of the proof. Okay, so basically those are technical details, much like how we set the 2 epsilon in our motivating example there to make some bounds go through. Okay, and the Learning from Data book contains the full proof of that. If you want to check the full proof, go check the book. You can, if you haven't bought the book, you can actually get those within the library or in my lab, where we have a few free copies there for people to watch. Is the newer bound tighter than the older bound? Okay, now first thing, we need to say which one is the older bound. There is a version of the bound that's not true. What's not true? If we directly plug an edge of n into the bound, it's not true. It's just a motivating question mark bound that I try to motivate you. Okay, so in this sense, the bound is not true, and therefore we should call it the wrong bound, not the older bound. Now, if you mean the older bound, is the new bound tighter than the older bound? And the short answer is no. It's actually looser than the older bound, and that's why we're trying to correct it. Okay, right? Okay, where we need to correct it into a form that it's true. The wrong bound is not true, and therefore you can say that it's arguably too tight, so it's not true, and therefore we need to loosen it in some sense. That's one direction of answering. On the other hand, if you mean the older bound being the union bound, the multiple being halving, then we get something tighter, because for that bound, if big M equals infinity, you get something very, 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 very loose, and we're tightening. Okay, so to answer your question, we really need to know which old bound you're meaning there. If your old bound means multiple being halving, we get something tighter. If your older bound means the wrong bound, then we're getting something actually looser, but correct. Is it practical to ask for n more data? Practical? No. Okay, so we are imaginarily asking the God for more data to carry out the analysis. Okay, we're not saying in practice you can always get n more data. No, we're just think about the proof as something like this. Imagine you can get n more data. Okay, then what's the kind of guarantee that you can get to get a bound on your original big N data? Okay, that's the core concept behind the proof. Okay, I seem to be able to answer all the questions here on Slido. Thank you for many of your inputs, and I understand that this part of the lecture is very challenging. So for challenging lectures, it's generally not that easy to understand all of them in real time, and I encourage you to catch up as early as possible by discussing with the TAs, by rewatching the lectures in English or maybe in Mandarin, by reading the textbook, and by sending emails or asking questions on the forum and so on, okay, to try to understand this part as much as possible. Because of two things. One, we will continue with this discussion next time, and you will not be able to follow our discussion if you don't understand this lecture completely. Two, this lecture would be an important part of your EVO homework 2. Yay! Which is arguably the most challenging homework that you would have in this class. And if you cannot follow the lecture, you would have lots of trouble finishing homework 2. And therefore, it's important to catch up as early as possible. Okay, that's the thing we want you to do. Very important for this week. Not just finishing homework 1, but try to catch up with homework 2. Okay, that's very, very important. Okay, thank you all so much for following the lecture today. Sorry, I'm a few minutes late. Okay, hope that you can solve homework 1 easily, follow with the lecture today, and be prepared for homework 2 next week. Yay! Okay, enough is enough. Thank you. Bye-bye.